The sun, seemingly unchanging. It is in fact a gigantic nuclear reactor. Its surface is in a constant state of flux. It sends out violent solar storms and streams of radiation hurtling toward Earth. Sunspots break through its fiery surface, and its giant magnetic field ripples throughout the solar system. We are only just beginning to understand the sun's impact on Earth. It brings havoc, but as global temperatures rise, could it also be our savior? The sun, a raging nuclear ball of superheated gas, so large, more than 1 million Earths could fit inside. And it makes all life on Earth possible. It powers the growth of plants and forests, providing a continuous stream of energy day in, day out. It has fueled our planet for 4.5 billion long years. To mankind, the sun's energy seems constant. Since the last major ice age 10,000 years ago, moderate temperatures on Earth have helped man to flourish and build technologically advanced societies. But this may not last forever. We are now beginning to understand that our planet's relationship with the sun is complex and turbulent. On a regular basis, solar storms rage. Gigantic clouds of plasma fly out from the sun's surface and strike the Earth's outer atmosphere, sometimes disrupting satellites and power grids.
Every minute, there's a battle going on between the sun's magnetic field and the Earth's magnetic field.
These sun surges emanate from deep within the sun, rising to the surface to create visible dark patches called sunspots. The activity of the magnetic fields waxes and wanes over an 11-year cycle. Solar maximum sees the greatest number of sunspots, and solar minimum the fewest. But what does this mean for us on Earth, 93 million miles away? Scientists are just beginning to understand that these magnetic fields may be much more influential than was once thought, and could have been responsible for historical climate change events.
From the historical record, changes in solar activity does have a measurable impact on Earth's climate globally.
A race is now on to understand this connection between the sun and the Earth, so mankind can prepare for all possible outcomes.
We have liftoff.
Space-based observatories provide us with a unique view of solar activity. In 2006, NASA launched twin state-of-the-art satellites to study at close hand solar storms and sunspots, visible signs of deep magnetic activity that affects the whole solar system. The scientists borrow a trick from 1950s B-movies to create a 3D image of the sun. They deployed 2 satellites orbiting in tandem, one in front of the other, so they can build a 3-dimensional image back on Earth. This 3D image will provide crucial new data on massive explosions of electrified plasma called solar storms. Billions of tons of superheated gas fly into space and buffet the Earth's atmosphere, creating the most dramatic northern and southern lights. Michael Kaiser of the Solar Terrestrial Relations Observatory, or STEREO.
We want to monitor these storms so that we can better predict them. These storms are basically electrical storms, and they can affect spacecraft, ground power systems. The GPS can be upset.
Solar storms are caused by lines of magnetic force ripping through the sun's gaseous surface and snapping, spewing out hot gases and a fierce stream of charged particles, the most powerful type of what's called solar wind. Some storms take 2 days to strike the Earth, while very large ejections arrive in only 12 hours. STEREO could give us time to put satellites and electric power grids into safe mode and move astronauts into protected sections of the space station.
The ones we're interested in, the ones coming right at us, are particularly difficult to estimate the speed and velocity.
A simple demo shows how two satellites allow scientists to calculate the speed of this solar wind. Michael Kaiser ejects a jet of liquid at a plate of glass. From the front, it's difficult to measure the speed. This is the way older satellites used to view solar storms. But from the side, you can measure 2 points along the projectile and calculate the speed more easily. Studying solar storms not just from the front, but the side as well, doesn't just reveal their speed, it also shows where they come from. The answer turns out to be the area around sunspots. These dark spots on the sun's surface were shrouded in mystery until the 20th century, when scientists realized that they were connected with the way the sun generates heat at its core. Once scientists understood that the sun got its energy from nuclear reactions, the answer became clear. Nuclear fusion within the sun creates the conditions for powerful magnetic effects. The currents of superheated gas generate intense magnetic fields. As the sun's interior churns, vast loops of magnetic force appear, merge, and disappear, creating sunspots. Luckily, there's a way to visualize it right here on Earth, in the comfort of your own kitchen. NASA astronomer Sten Odenwald compares magnetic field lines to spaghetti.
The surface of the sun is very hot gases that are turning over in a boiling motion. What you're seeing in the pot of water is the convecting water coming up to the surface and releasing its heat and then sinking back down into the pot to get reheated.
The rolling strands of spaghetti are like the magnetic field lines churning beneath the sun's surface.
And these fields come to the surface, get concentrated into sunspots and flares and things like that.
The turbulence that causes sunspots doesn't just come from heat, it also comes from the sun's rotation. On solid planets like the Earth, every part of the planet rotates uniformly. But the sun is a ball of gas, and the same rules don't apply. The equator rotates in 25 days, but the poles take 35 days. The magnetic loops get stretched and distorted as it turns, and where they break the surface, sunspots emerge. Sunspots are immense. A spot can be anything from the size of the African continent to 30 times as wide as the whole Earth. It's thought that the bigger the spot, the bigger the magnetic instability that lies beneath, leading to more severe storms and powerful invisible radiation, like X-rays and gamma rays. And what's weird is that they are not dark at all. They just appear dark because of the brightness around them. In fact, a sunspot is 10 times brighter than the full moon. Solar physicist and expert on sunspot prediction, Leif Svalgaard, can demonstrate how the eye is tricked by this illusion of light, using a small light bulb and an overhead projector. A sunspot is very hot, around 8,000 degrees. It's represented by the glowing filament of this light bulb. This appears bright until Svalgaard turns on the overhead projector, which represents the sun.
And if you now switch on the rest of the sun, at 10,000 degrees, you will see that the sunspot now appears dark. So it's only by this contrast that it looks dark.
Sunspots are in effect a window on the sun's hidden magnetic activity. But they may also be an indicator of another more profound effect that science is only now beginning to understand. Unknown to medieval astronomers, a dramatic decrease in the number of sunspots may have been linked to a period of significant climate change, now known as the Little Ice Age, a harrowing time when numerous crops failed and some lands became uninhabitable. Sunspots are as familiar to astronomers as the planets and our moon. Up until the middle of the 19th century, they were just an astronomical curiosity. But now, some scientists think that sunspots are visible signs of a mysterious mechanism that spawned significant climate change in Earth's past. Their theories are based on the frequent correlation between sunspot numbers, as recorded by astronomers down the centuries, and climate records. Scientists are now discovering that solar variation affects our climate in complex and subtle ways.
The number of sunspots on the surface, the number of solar flares, the amount of ultraviolet light does have a measurable impact on Earth's climate.
The first record of sunspots dates back to 800 BC. Galileo was the first astronomer to study sunspots scientifically, famously drawing the position of the spots in his notebook. Astronomers' records show that between 1645 and 1714, the numbers were so low as to be almost absent. At the same time, Europe and North America was suffering a period of cooling known as the Little Ice Age, which lasted for around 500 years. But during the Little Ice Age, there was a shorter period of brutal cold, lasting for just over 70 years, known as the Maunder Minimum. One winter during the Little Ice Age, it was possible to walk all the way from Manhattan to Staten Island over the ice. And in London, the Thames froze over for months on end. Londoners even held ice fairs out on the river. The fact that part of this period of severe cold was matched by low sunspot numbers has intrigued scientists ever since. A leading expert on how solar radiance influences our climate, Judith Lean.
There's a lot of anecdotal evidence that connects the sun's variability and climate change through indirect indicators of the sun's brightness and also of the surface temperature. And it's a very controversial topic because to understand it properly, we really need long-term records of the brightness changes itself and of the climate change.
Scientists needed more data, and that was a challenge. Galileo's records are the earliest that give us a clear idea of how much activity was going on. But now scientists have records of sunspots going back over thousands of years. They learned the key was not to look at sunspots themselves, but rather at an astronomical phenomenon which at first glance appears unrelated: cosmic rays. Scientists believe that cosmic rays originate from sources all over the universe, such as massive exploding stars. Charged particles fly out at close to the speed of light. Space is full of cosmic rays. They bombard the Earth continually, and we can measure the intensity of this bombardment over time. Cosmic rays collide with molecules in the atmosphere to produce isotopes, such as carbon-14 in tree rings and beryllium-10 in ice deposits. Thousands of years later, scientists can unearth the hidden records of this bombardment by measuring levels of these isotopes.
We can use carbon-14 to trace the sun's activity cycle going back literally thousands of years. And that's really amazing.
Levels of carbon-14 and beryllium-10 are affected by the sun's magnetic field in space. The sun's magnetic field is vast. Normally it extends 8 billion miles into space. But when the sun is more magnetically active, it stretches to 10 billion miles. Because cosmic rays are charged particles, magnetic fields deflect them. The more magnetically active the sun is, the more cosmic rays are deflected, leaving fewer markers in ancient trees and ice cores. Magnetism has long been used to deflect charged particles on Earth, too. Cathode ray tubes in TV sets do so to create a picture. Oxfordshire, England. At the Rutherford Appleton Advanced Physics Laboratory, British professor Mike Lockwood demonstrates how easily magnetic fields deflect cosmic rays. A simple beam of electrons created in a laboratory behaves in the same way as cosmic rays upon hitting the sun's magnetic field. This glass case contains a green beam of electrons that are physically similar to cosmic rays. Lockwood will simulate the sun's magnetic field with two metal coils.
When I pass electric current through a coil, I generate a magnetic field. And so if I turn the current up, I increase the magnetic field inside the bulb, and I start to deflect the beam. And the more I turn the current up, the larger the magnetic field and the more the deflection.
Just like the experiment, when the sun is at its solar maximum every 11 years, the sun deflects more cosmic rays away from Earth. So the number of sunspots appears to be directly related to the amount of cosmic ray deflection. This all ties together with events during the Maunder minimum. The carbon-14 data from trees reveals that the cosmic ray flux increased during this period, which suggests the sun's magnetic field became less active and the spots almost vanished from the surface.
We had the Maunder minimum, where there were few sunspots and a higher than normal flux of cosmic rays. And we can find other examples like that, and we can find periods like recent times when the solar activity has been unprecedentedly high and the cosmic rays have been low as a result.
Thanks to cosmic rays, we have a historical database by which to investigate the changes in our climate and weather systems. Man-made global warming is an indisputable fact. But could solar variation contribute to future climate patterns as well? Solar physicist Leif Svalgaard predicts that the solar cycle could plummet after decades of activity.
There is a chance, since we have had a few large cycles, that the next one will be small.
Svalgaard uses the strength of the magnetic field at the sun's poles to predict future sunspot activity. These fields shown are responsible for recycling sunspots. As a spot fades from view, its residual magnetic field is swept toward the poles by a surface current. At the poles, the flow of magnetic energy sinks to near the core and then moves toward the equator. Then, scientists believe, it begins a return journey toward the surface, being rejuvenated with more magnetic energy along the way. Svalgaard thinks that the amount of magnetic flux that accumulates near the solar poles around sunspot minimum is a measure of how many spots the next maximum will have. More flux means more spots. But even his method is far from foolproof.
There's also a chance that there might be another big cycle before the next one after that being smaller.
One thing is very possible, and that is maybe the next sunspot cycle or the one after that might not come. We might have another one of these Maunder minimum conditions. We don't know. We can't predict things that well yet. But that's always there sort of as a possibility in the future. And we'd like to know if that's going to happen or not.
Every 100,000 years or so, the Earth goes through a major ice age due to a change in the shape of its orbit around the Sun. Our orbit isn't a perfect circle and fluctuates over time, putting the Earth either closer or further away from the Sun. At its most elliptical, there is a 23% difference in solar radiation between the two most extreme points in the orbit. Right now, it's only 7%, providing us with a temperate climate since the last major ice age. But what about other influences of the Sun, apart from these periodic changes in orbit and tilt? Are changes in solar radiance enough to affect our climate and weather patterns? The answer is, it depends how long the changes last. Sunspots change over an 11-year cycle. But that's not enough time for the small differences in energy output to make a difference. Our planet just can't heat and cool that fast. This is because the oceans absorb lots of energy and take decades, even centuries, to reflect the changes.
There's no doubt that if the solar output decreased by enough on those timescales, then the Earth would cool in response.
The 11-year cycle has little impact, but that's not the end of the sunspot cycle. Other trends are also found in the records. The Maunder minimum may have been a result of a longer cycle, and that could be long enough to make a real difference. Exactly How much difference?
But the problem is, although you can trace the activity of the sun, it's very hard to trace how the climate of the Earth has changed in step with that.
Accurate climate records going back thousands of years will be the only way to understand if the sun periodically has bigger cycles and potentially a larger impact on global climate. And that's what two American scientists think they have discovered deep in the caves of New Mexico. Scientists are beginning to understand how the sun's magnetic fields may have profound effects on Earth and our solar system. In the past, changes in the sun's magnetic fields may have affected climate and weather patterns for decades and even centuries. The frequency of sunspots, the physical sign of magnetic activity in the sun, seems to match dramatic changes in our climate over the last millennia. But how can we know what the weather was like hundreds and thousands of years ago? Prior to the 19th century, accurate human records of drought and rainfall don't exist. Paleoclimatologist Yamani Asmaram and his colleague Victor Polyak of the University of New Mexico have found an ingenious way to accurately calculate the weather from our Earth's past, using stalagmites in ancient caves.
When you look at the climate record over 10,000 years based on stalagmites, the match is surprising and also fairly robust.
The deep caves of New Mexico in the southwest United States have preserved a perfect record of changes in climate. Through them, these scientists have established a climate record for the American Southwest over a 3,000-year period during the late Holocene. This covers the most recent period of Earth's climate history, from when the last ice age receded.
One of the important attributes of stalagmite is that you can obtain absolute ages precisely, and they also contain annual laminations, just like tree rings, and they contain evidence of climate change at a fine scale.
But to retrieve the data, the samples need careful preparation. The stalagmites go through a three-stage process.
This stalagmite grew from 3,000 years ago to present, and it exhibits annual bandings.
First, a drill grinds out some sample powder.
This is more than enough powder to establish an accurate age for that particular layer.
Next, Polyak mixes the sample with chemicals. This separates the sample into uranium and thorium isotopes. Lastly, the elements go into a mass spectrometer. This process measures the amount of uranium that has decayed over time and the amount of thorium isotopes produced. Because they know how long decay or production of these isotopes takes, they can work out exactly how old the sample is. They can also work out from its chemical and mineral composition how dry the climate was during that particular year. Amazingly, the periods of drought shown by these records accurately match sunspot activity as measured by carbon-14 data. Stalagmites provide accurate records going back hundreds of thousands of years. The scientists' unique methods may explain the mysterious disappearance of an ancient Native American civilization 330 miles north of the caverns in Chaco Canyon. The Chacoan people settled here in northwest New Mexico in 850 AD.
The Chaco complex is considered one of the regional centers for ancestral Americans. At its time, this was a center of activity, very complex, comparable to other communities the world over.
Then suddenly, 400 years later, experts believe the climate dried up dramatically. The Native Americans left the canyon for good.
Unfortunately, in spite of their sophistication, they didn't have the adaptive capability to survive such a dramatic climate change.
The stalagmites recorded these changes with incredible accuracy and revealed that around the year 1250, there was indeed a severe drought. But did the sun force the climate to change? Did it simply produce more heat than normal during this dry period? A simple way to measure the sun's output is to look at how much a small area of Earth is heated during the 11-year solar cycle. On a sunny day, every square yard of this planet's surface receives 1,000 joules of energy per second from the sun. This solar energy, or radiance, is partly absorbed and partly reflected back to space. Over the 11-year solar cycle, this varies by a surprisingly tiny amount. A simple way to demonstrate this change in output is with this basic electric heater, which produces an equivalent amount of power as the sun does per square yard. Solar physicist Joanna Haigh shows us how little the difference in heat output really is.
So we can see the intensity that's arriving from the sun. Now, how much of that is varying over the 11-year solar cycle? It's only about 0.1%, and we can see what that means by looking at the radiation coming out, or the light coming out of this little torch here.
Incredibly, this small flashlight generates the same amount of extra energy as the sun does at solar maximum compared to solar minimum.
You can see it's a very small amount, and it's very difficult to understand how this very small change in solar radiance could account for any significant impact on climate.
So, if, as Haigh contends, 0.1% is too small to cause the climate change we've seen in the past, then what mechanism is driving those changes in climate as confirmed by records? Haigh has a theory. It might not be the sun's brightness that causes the change. It might be another aspect of the sun's energy altogether, one we can't see. Perhaps increases in ultraviolet radiation lead to significant changes in weather and climate. Scientists have discovered a possible link between the dark solar spots of the sun and historical periods of dramatic climate change. But the sun's natural heat output varies very little over an 11-year cycle. People often refer to the sun as a solar constant, as expert Barbara Thompson of NASA testifies.
The solar constant is not really a constant. It's fairly steady. So you'll get throughout the solar cycle variations in how much solar output the sun is putting out. It's not a huge change. You actually need some pretty sophisticated instruments just to measure the change.
So why is there a statistical link between solar activity and historical changes in climate and weather? The answer may lie in the fact that the sun doesn't just generate heat. The sun also generates radiation, with wavelengths in the invisible end of the spectrum. One such type is best known to sunbathers as ultraviolet radiation. We don't see UV rays or microwaves or X-rays for that matter. But the sun generates them along with heat and visible light. Scientists discovered that emissions of these invisible waves also fluctuate over the 11-year solar cycle. UV rays can increase up to 100% from solar minimum to solar maximum when the sun's magnetism is at its strongest. Significantly, recent satellite observations of the sun show it emits more UV when there are more sunspots. So sunspots mean increased UV radiation striking the Earth's atmosphere. This image of the sun, taken from NASA's SOHO satellite, shows the UV rays emitted during a solar storm. And this is the amount of UV radiation emitted during a quiet period of solar minimum.
And by the time you get to the X-ray region, it's varying by 100%, so it's doubling from solar max to solar min over the 11-year cycle.
What other effects could increased amounts of UV have on our climate? UV reacts with oxygen, the chemical element in the atmosphere that gives us life and forms ozone. A layer of ozone surrounds the Earth, providing a blanket of protection.
So on my hand here, I've written a secret code, which you can't read. And you can't read it even if I shine the torch on it. There doesn't seem to be anything on there. If, however, I shine the ultraviolet light, you can see secret code. And what's happening here is that the chemicals that are in that ink that's on my hand are responding specifically to ultraviolet light, in rather the way that ozone in the stratosphere is going to absorb ultraviolet light and not normal radiation.
The ozone layer is located around 12 to 30 miles above the Earth's surface. It protects us from the worst effects of UV, but it also has another important atmospheric role to play as a greenhouse gas.
So it traps heat radiation that comes from below, and it acts like a blanket and is warming the climate.
When electromagnetic radiation peaks at solar max, ozone levels in the stratosphere rise by about 3% due to the increase in UV rays reacting with the oxygen molecules. The theory is that this increase in the ozone, along with the extra UV, creates a warm layer which traps air in the lower atmosphere.
So if we change the properties of the stratosphere, if we change its temperature or its height, that affects the circulations of the atmosphere below.
The movement of the hot air in the tropics pushes storm tracks toward the northern Atlantic and Pacific Oceans, which would explain why the Little Ice Age was localized to those areas. For now, scientists can't prove that UV has a large enough influence to cause some of the more dramatic swings in our climate.
Variations in solar activity can definitely affect the climate. The problem we have is in understanding how large these variations are.
So UV radiation is a possible cause of localized climate change. But one lone British scientist thinks there's something else about the sun that affects our planet. Atmospheric physicist Dr. Neil Arnold believes that the solar wind itself might alter climate. The solar wind is made up of a stream of charged particles, high-energy electrons and protons, expelled by the sun constantly, and especially strong during periods of high magnetic activity. Arnold believes that the solar wind collides with Earth's upper atmosphere, called the thermosphere, which in turn stirs up the climate miles below, causing global warming effects.
The solar wind interacts with the Earth's upper atmosphere quite freely, creating big changes there.
This idea flies in the face of conventional thinking about solar wind.
Most scientists would conceive no possibility of it being able to make a significant change to the weather and the climate.
To understand the theory, we have to understand how our climate is kept in balance by Earth's rotation and gravity. These create an effect called the Coriolis force. Our planet's atmosphere has a fine equilibrium. Without the Coriolis force, hot air from the equator would rush to the cooler poles, destabilizing our climate. Instead, atmospheric circulation travels from east to west around the globe, kept in balance by the Earth's rotation. We can demonstrate the Coriolis force by showing how a ball reacts to being rolled in a straight line on a children's merry-go-round. This reveals that the ball rolls in a curved trajectory rather than running straight off the surface of the merry-go-round. So the Coriolis force prevents the circulation of atmosphere from heading toward the cooler poles, driving the system east to west. But Arnold believes that when the solar wind emitted from clouds of plasma strikes the thermosphere, it disrupts this carefully balanced Coriolis force. The hot air moves from warm regions toward the cold polar regions and vice versa. The whole atmosphere is disrupted by the hot air now circulating toward the colder poles. According to Arnold, this overall stirring up prevents some heat from being radiated back into space, raising global temperatures. It's a controversial theory, as solar storms can hit the Earth on a daily basis.
People are skeptical that things happening in the upper atmosphere around a few hundred kilometres, where, for example, low Earth orbiting spacecraft are, actually has an impact on the surface.
If solar storms and UV rays aren't the cause of historical climate change, then what other mechanism could be responsible? As we have seen, Paleoclimatologists have well-established records of sun activity over centuries by using isotope analysis and radiocarbon dating. When solar activity is high, the sun's magnetic field balloons, deflecting galactic cosmic rays. When the solar activity is low, more cosmic rays buffet the Earth. Could cosmic rays themselves be the missing link between solar activity and global climate change? The sun is the most powerful object in the solar system. Scientists are just beginning to understand its effects on our planet. It appears that historical changes in climate are linked to the strength of the sun's magnetic fields. Records from the last 1,200 years have shown an emerging pattern of solar influence. Around 800 AD, there was a period of unusually warm weather that lasted for around 400 years. Then the climate seesawed back to cooler conditions. By around 1250, the Viking colonies on Greenland had turned from fertile farmlands into barren wastelands. In the 17th century, London saw the Thames freeze over. Up until the 20th century, the cause of the swings of temperatures was a mystery. The sun seems to be a catalyst, but exactly how it has driven past climate change events is still unknown. One possible explanation involves UV rays and solar storms disrupting our weather systems. But there could be a more subtle and surprising cause, one that begins its life outside our solar system, deep in space. The amount of interstellar cosmic rays hitting the Earth is regulated by the strength of the sun's magnetic field at that particular time. Isotope analysis on ice and tree rings gives us an extraordinary record of this. But what if the cosmic rays themselves affect our climate and weather systems more directly? Could these energetic particles emanating from exploding stars be the actual mechanism behind some climate change? The first clue may be linked to an everyday meteorological phenomenon: clouds. Low-level cloud coverage generally exerts a cooling effect on the Earth's surface. As cloud coverage increases, heat from the sun is reflected back into space. This allows the Earth's surface and oceans to cool down. It's thought by some that a 2% increase in low cloud cover would reduce temperatures back to pre-industrial times. The link between cloud coverage and climate change intrigues Danish physicist Henrik Svensmark.
2% doesn't sound like very much, but it's actually quite important for climate.
Clouds form when rising air from the heated surface of the Earth cools to a point where some of the water vapor molecules clump together faster than they can be pulled apart by their own energy. The water vapor then condenses to form cloud droplets.
With this simple device here, where I have a bottle with a little bit of water in, I can try to demonstrate how clouds form.
First, the water saturates the air inside the bottle. The conditions are now right for forming a cloud. All that's needed is the addition of some tiny particles to act as seeds for the water molecules to clump around. Svensmark will use smoke.
And then I try to do a super saturation by just pressuring this, and then I release, and you'll see that it starts getting white when I release. And that's because there's a supersaturation of vapor and it sticks to these small particles.
The experiment shows that the introduction of a few small particles in the atmosphere could encourage clouds to form. Seeding of clouds happens naturally in our atmosphere. But what if the seeding was supplemented from outside our atmosphere? Svensmark believes that an old theory that cosmic rays can seed clouds might explain climactic periods like the Maunder minimum, a time when the volume of the cosmic rays hitting the Earth was very high.
So you will actually have more clouds on the Earth, and that will give you a cooling of the temperatures.
For the cosmic rays theory to be credible, the team first had to look for a statistical link between cloud coverage and a variation in cosmic rays flux. They analyzed weather satellite records from 1979 to 1992. This period was long enough for the Sun to have completed the well-established 11-year cycle of activity. Svensmark claims to have found that the Earth was 3% cloudier at solar minimum, a statement some scientists dispute. Cosmic rays are invisible to us, but they can be seen indirectly in this special laboratory chamber.
Inside, we have a very high supersaturation of, it's actually alcohol. And when a charged particle goes through, like a cosmic ray, it creates like a contrail of small droplets in its wake. They are everywhere. Maybe 140 particles hits me every second and going straight through my body.
Like any theory, Svensmark needed evidence to back it up. He needed to prove how a cosmic ray could act as a seed in saturated air in the laboratory. In 2005, his team of Danish scientists designed an experiment to see if cosmic rays could seed clouds. The larger chamber was built for testing at sea level, while a smaller one is designed to be taken underground to screen out the rays. The idea is that scientists inject air and trace gases like sulfur dioxide into the tank to imitate the air above the ocean. Instead of the sun, they use a UV lamp attached to one end. The last element doesn't need any assistance. Cosmic rays penetrate the steel outer casing naturally. As cosmic rays naturally strip electrons from the artificial air, clumps of molecules form around these tiny charged particles. These cloud condensation nuclei are recorded by a special counter. The Danes have shown perhaps the very first stage of the formation of cloud condensation nuclei. But they need evidence that the particles could grow bigger before forming water droplets. And that requires more research in more controlled conditions. Such research is planned for 2010 and will take place at CERN in Switzerland, in the world's largest particle accelerator, sunk deep underground. A beam of accelerated particles simulating cosmic rays will be fired into saturated air. Only then could we discover if the Danes' small particles really can grow to the size where clouds begin to form.
This will be a very interesting experiment because this whole area is something we know very little about, that it could confirm the theory that they could grow into something big enough to help clouds form.
Scientists are only just discovering the extent to which our sun influences Earth's climate and weather patterns. 30 years ago, few thought that solar variation had any influence on climate variation, but a small growing band of scientists believe that it certainly does. If the solar cycles are really helping to drive our climate, then the activity of the sun will be crucial to the Earth over the next century.
We're beginning to understand there are these subtle links between the solar wind and aspects of our atmosphere.
Man-made greenhouse gases are warming our planet, but could big changes in the sun's magnetic activity also be an important factor in the future? If there is a crash, then global warming may be slower than expected, potentially saving parts of the globe from flood and famine. Despite this possibility, many believe that carbon emissions would still need to be cut.
We need to still continue with that, because when the sun finishes going through its 100-year period of low activity, we're going to be right back to where we started before with a vengeance.
We know we have the power to change our planet's climate. It's a power we need to use responsibly. But ours is not the only power at work.
Variations in the sun have happened over eons, and changes in the energy coming out of the sun will affect climate on Earth, because the energy is the main driving force for climate.
The sun has been influencing the long-term climate here on Earth for as long as we've measured. It could be that the less magnetically active it is, the cooler we become. We don't fully understand how it happens, be it UV rays, solar wind, or even cosmic rays. But one thing is certain. Our well-being and the well-being of planet Earth is dependent on the sun in ways we're only now beginning to understand.